Assalamu alaikum everyone. In this video tutorial, we're going to learn how to calculate the heat of reaction for any other condition, rather in other condition than the standard condition. So in the previous video, we have learned that the standard condition for the heat of reaction was at 25 degrees Celsius. So basically what we're going to learn in this video tutorial is that how to calculate the heat of reaction in any temperature other than the 25 degrees Celsius temperature. Okay, so here is an example that the standard heat of following methanol synthesis reaction, and the question demands us that we determine the heat of reaction at 800 degrees Celsius. Okay, so a quick recap of our previous video, that for any chemical reaction, take for example this reaction. For any chemical reaction, we use the heat of formation method in order to determine the heat of reaction of that chemical reaction. So for this chemical reaction, the heat of reaction at standard conditions was going to be the heat of formation for methanol, the heat of formation for methanol, and minus the heat of formation for carbon monoxide. And we also explained that why we always do output minus input in case of heat of formation. Okay, so that's all that we have learned in the previous video. Okay, so now we're going to learn about how to calculate the heat of reaction in any temperature other than 25 degrees Celsius. So basically what we're going to do here is draw a process path. Okay, so what is a process path? We don't know any process of calculating any heat of reaction any temperature other than the 25 degrees Celsius temperature. So what we're going to do, we're going to uh, perform this chemical reaction at 25 degrees Celsius, and then we're going to determine from that value of 25 degrees Celsius, then we're going to determine what the value is going to be at 800 degrees Celsius. So here is a more elaborate explanation of how we're going to do that. So first of all, we have got our reactants here, right? Carbon monoxide and hydrogen gas. So these reactants are at 800 degrees Celsius. So now we're going to cool these reactants. We're going to cool these reactants to 25 degrees Celsius. We're going to cool these reactants to 25 degrees Celsius. 25 degrees Celsius. Perform the chemical reaction at 25 degrees Celsius. That is methanol in its gaseous state, and then we're going to elevate the temperature of the produced methanol up to 800 degrees Celsius. And then our proposed chemical reaction is actually complete. I have already told you that enthalpy is a state function. It does not depend upon the path. It only depends upon the initial minus final value. So it doesn't depend how do we get to the final value. So we can easily take this process path method, and what we do, let us recap that what we're going to do in this process path method. First of all, we're going to cool down the reactants from 800 degrees Celsius to 25 degrees Celsius. Why did we do that? Because only at 25 degrees Celsius we know how to calculate the heat of reaction of any chemical reaction. So that's why we're cooling the reactants, and then we perform the chemical reaction at 25 degrees Celsius, and after the formation of the product, then we take the product and then elevate it up to 800 degrees Celsius, and then our proposed reaction gets complete. Okay, so for the first path, there is going to be an enthalpy change for the cooling of reactants from 800 degrees Celsius to 25 degrees Celsius, and in the second step there is going to be another enthalpy change for the reaction that's taking place, and in the third step there is going to be another enthalpy change because of the rise in temperature of the reactant of the products because of the rise in temperature of the products. Okay, so we're going to state this as delta H1, we're going to state this at delta H2, and we're going to state this at delta H3, and this one is the delta HR. So from this process path we can easily state that the overall enthalpy change, from this process path, we can easily state that the overall enthalpy change, delta HR, is going to be delta H1 plus delta H2 plus delta H3, right? the overall enthalpy change is going to be delta H1 plus delta H2 plus delta H3, and we can restate the delta H2 as delta HR not, because it is the chemical reaction happening at the standard condition, right? So we can rename it as delta HR naught. Okay, so basically instead of delta H2 we can also write delta HR naught here. Okay, so now another question arises that we have learned how to calculate the delta HR naught, but how are we going to calculate the enthalpy changes for the cooling and the rise in temperature? How we're going to do that? So basically in open system energy balance, the calculation of enthalpy is simple. For the calculation of enthalpy, the main equation is that dH, the differential change in the enthalpy, is equals to the heat capacity at constant pressure and times the differential change in temperature. So what is the heat capacity in constant pressure? Basically the amount of heat any substance absorbed in order to improve its temperature by a unit amount. That's the heat capacity at constant temperature. So an important note, we're considering at the pressure to be constant. Pressure, the pressure in the overall process is constant here, and we're going to see in further calculations that the pressure is not necessarily has to be constant. The value of Cp, or the heat capacity in constant pressure, can be applied for ideal gases and for other gases that have really high pressure. Okay, so theoretically the pressure doesn't have to be constant, not necessarily, it doesn't have to be constant. Okay, so we're going to use this calculation, we're going to use this equation for calculating the change in enthalpy for the cooling of the reactants and for the heating of the products. Okay, so if we integrate this equation, we're going to get the change in enthalpy, which is delta H, which is going to be the integration of dH, and that's simply going to be the integration of Cp dt from temperature 1 to temperature 2. Okay, and sometimes the Cp, the heat capacity at constant pressure, it's a function of temperature itself. So sometimes the Cp value will be a function of temperature, which will look something like this: A plus Pt times dt. Okay, so these sort of integrations are really elementary for now, for us now. Okay, so we're going to calculate the we're going to calculate the enthalpy changes using these equations, and then we're going to calculate the heat of reaction at standard condition, and then we're just going to add all these enthalpies. Okay, so after building a process path, we're going to build another important, really important thing known as the enthalpy table. Enthalpy table. And before producing an enthalpy table, we must state what our reference state is. We have already stated that our reference state is at 25 degrees Celsius. Okay, so our reference state is going to be all the substances here: carbon monoxide, hydrogen gas, and methanol gas. As they are all in the gaseous state, our reference state is also going to be that carbon monoxide, hydrogen in the gaseous state, and methanol in the gaseous state, and they're at 25 degree Celsius. Okay, so now we're going to form an inlet outlet enthalpy table, and let's see what that looks like. Okay, so inside the inlet outlet enthalpy table, there is going to be a column of components. There is going to be a column for the moles input. There is going to be a column for the enthalpy input. There is going to be a column for moles output, and there's going to be a column of enthalpy output. Okay, so what are the components here? The components are carbon monoxide, hydrogen gas, and methanol. It's not necessary to mention the states here, as we have already mentioned the states in our reference state, so it's not necessary to mention the states of the components here. Okay, so what we're going to input here in the column of moles input, so as there is no specific amount of moles input here, we're just going to take the stoichiometric amounts. So we're going to assume that there is 1 moles of carbon monoxide that was being input, and there are 2 moles of hydrogen gas that were being input, and no amount of methanol was being input to the reactor. Okay, and then the H input. Okay, so what was the enthalpy of these substances while they were being input? So H input is going to be the enthalpy at 800 degrees Celsius. Okay, H input is going to be the enthalpy at 800 degrees Celsius. Okay, so this is going to be H1 specific. Let's assume this is H2 specific, and this is not going to have any value of enthalpy as there was no methanol present at the input stream, and in the output stream there is no carbon monoxide and there is no hydrogen gas. Again, as there is no specification of the percentage conversion, we assume that 100% of the reaction has been converted into product, and so the methanol is going to be 1 moles according to the stoichiometry of the reaction. Okay, so there is not going to be any value here, and there is H3 here, which is at also at 800 degree Celsius. Okay, all right. So now we're going to have to calculate H1 specific, H2 specific, and H3 specific. Okay, so this hat here, it okay, so these hats here, these indicates the specific amount of enthalpy, which is enthalpy per mole. Okay, enthalpy per mole or enthalpy per kilograms. But basically, we're going to calculate here enthalpy per moles, and then we're going to multiply it by the amount of mole that has been input to this reaction. All right, so first of all, we're going to calculate H1. So we're going to use this equation for calculating H1 using CPDT from T1 to T2, from temperature 1 to temperature 2, and again we're going to use the data booklet from Smith, from the book of Smith, and at the table C1 here, the heat capacity functions for various substances are given here. So the heat capacity functions for carbon monoxide, the heat capacity function is given here as 3.376 times plus 0.557 10 to the power minus 3 T dt, and we're going to multiply 8.314, the molar gas constant here, because the heat capacities that are given here, the values for heat capacities is in the form of Cp divided by R. So R is the, here 8.314 is R is the molar gas constant, molar gas constant. Okay, so R is the molar gas constant that we have added here. So now that we have added the molar gas constant, so we're going to calculate the value. We're going to calculate the value of this part from temperature 1, which is our reference state, which is at 298 Kelvin. Where did we get this 298 Kelvin? 25 degrees Celsius. We have converted into Kelvin temperature, and then we're going to elevate it up to 800 degrees Celsius. Notice a very important thing. Our main process path, in the main process path, we have stated that we're going to cool down the reactants from 800 degrees Celsius to 25 degrees Celsius. But in this calculation, we are basically elevating the reactants from 25 degrees Celsius to 800 degrees Celsius. So in order to make it in correspondence to our actual process path, we're going to have to add a negative value here. We're going to have to add a negative in before the value here. We're going to show that in further calculations. So let's see what, so we can calculate the H1 specific here, right? There's going to be a value here. Okay, so this one is 24.212 kilojoules per mole, and for H2 specific, we're also going to use the CPDT function uh, from T1 to T2 CPDT, and for H2, basically for hydrogen, what is the CP function for hydrogen? For hydrogen, the CP function is 3.249 plus 0.422 into 10 to the power minus 3 T, integrating from 298 Kelvin to 800 plus 273 dt times 8.314. Okay, so this value is basically um, 2.742 kilojoules per mole. Okay, so this value is basically 2.742 kilojoules per mole. Okay, so this is for delta H2, and now we're going to calculate delta H3. Let's calculate H3 specific here. H3 specific also going to be from T1 to T2 CPDT. So the function for methanol is 2 point integrating 298 to 800 plus 273 and 2.211 plus 12.216 into 10 inverse of 3 times T times dt times 8.314. So this value is going to become to be 68.203 kilojoules per mole. Okay, so this is 68.203 kilojoules per mole, and these are H1, H2, and H3. Okay, so now what's left to calculate is so we have calculated the necessary components for calculating delta H1. We have also calculated delta H3, and now what is left is the heat of reaction at 25 degrees Celsius. So if we calculate the heat of reaction at 25 degrees Celsius, what's gonna happen? So the heat of reaction at 25 degrees Celsius, delta H R naught, it's going to be the heat of formation for methanol, the heat of formation for methanol, negative the heat of formation for carbon monoxide. Okay, the heat of formation for methanol, negative the heat of formation of carbon monoxide. Hydrogen is not going to be considered here as it is a diatomic molecule. Okay, so the heat of formation for methanol, we're going to take that from the table of Smith, which is table C4 of Smith. The heat of reaction for methanol in the liquid state is 200.66, and the heat of formation for carbon monoxide is minus 90.135. So this is the amount of kilojoules, of course, kilojoules. We can say per mole here because kilojoules, because we have already multiplied it by 1, so we not necessarily need to say kilojoules per mole here. So delta H R naught we have also calculated here, minus 90.135. So now what we're going to do is that the total delta H is going to be, the delta H R is going to be delta H1 plus delta HR naught plus delta H3, right? So for delta H1, what we have done, for delta H1, we're going to have to take the negative value of the mole numbers multiplied by the specific enthalpy. So what I mean to say is that we have calculated H1, but we have calculated H1 specific kilojoules per mole. We have also calculated H2, but we have calculated H2 specific kilojoules per mole. So we're going to have to multiply these specific enthalpies with their corresponding mole numbers. So what we're basically doing, and then we're going to add those mole numbers. So what we're basically doing is that we're doing N2 H2 specific at input plus N1 H1 specific at input, and we're taking a negative there because we have calculated the enthalpy assuming that we are elevating the temperature from 298 Kelvin to 800 degrees Celsius, and then the heat of reaction value that we have gotten here, and then the H3 values, which is going to be N3 H3 specific at output. So basically if we just put these equations in a standard part, this equations is going to be that summation of N out H specific out minus summation of N in multiplied by H specific in plus the heat of reaction at the standard condition. This is the standardized formula for calculating heat of reaction at any temperature other than the standard temperature. Okay, by simply adding these values we can calculate the heat of reaction, the total heat of reaction. So what's going to be the total heat of reaction? So negative, the heat of reaction values were 24.212 and 2.742. So 24.212 minus 2 times 2.742 plus heat of reaction value was minus 90 point something. What was it? Minus 90.135 kilojoules. Minus 90.135 kilojoules plus the output enthalpy was 68.023. 68.023. So the ultimate value is going to be, so it's going to be minus 51.881 kilojoules. So that's delta H R. Okay, so this is the calculation. This is the method of calculation for heat of reaction at any other temperature than 800 degrees Celsius. So the process here is really simple. We actually constitute a process path, and then we form the inlet outlet enthalpy table, and then we calculate the enthalpies, and then we add all those enthalpies. I might do some calculation mistake here. That's all up to you. My main goal is to familiarize with you the process, the main theories with which you can calculate the values. Okay, I might do some calculation mistakes, and if I do, then please feel free to notify me of my mistakes. Okay, so in the upcoming videos we're going to talk about more complex theories of heat of formation, heat of reaction, more complex theories, like what if the reaction does not uh, what is the reactions does not goes to full completion. What if the reaction, what if there is only a 80% conversion, or what if there is a 30% conversion in the reaction? What we're going to do then, how we're going to calculate the heat of reaction then, and what if the reactants are in a certain temperature but the products are in another temperature? So what we're going to do then? Okay, so there are some complexities and some complex realities that can be constructed using the heat of reaction methods. Okay, so in the upcoming videos we're going to talk about the further explanation. We're going to talk about further complex realities regarding the heat of reaction methods, and we're going to talk about the process of calculation, the little bit of modification in this process due to those calculations, but the fundamental process we have discussed here in today's video. So till then, everybody stay tuned to my channel and enjoy learning. Assalamu alaikum.